In science labs, we don't often use this percentage. I mean, it's not like we don't, but we use a different thing, and it's called molarity. Okay, and you can probably guess where this is going. Molarity, yeah, it means it has moles in it. Okay, there's also another one called molality. There's even one called normality. We're not going to deal with those. You can save that for college, but we will deal with molarity. Molarity. And so it has moles in it. And so the definition of this is it's moles of stuff. It's supposed to be called solute, but I don't know who wants to call it solute. Moles of stuff, be salt or sugar or whatever. Moles of stuff divided by the volume of the solution. That gives you the molarity of the solution. And also say molar, 3 molar solution. Right? And that's molarity. Now, 2 important things about that. First of all, the volume has to be in liters. Right? That's standard. Molarity is measured in liters. Unfortunately, in our labs and in our problems, we're going to always see milliliters. So you're going to have to do a lot of conversion back and forth between milliliters and liters. And at this point in time of your careers, this should not be a tough thing, folks. But think about it. A milliliter is like this. A liter is like this. Okay, so are there 1,000 of these in one of these? I don't think so. Right? So there's 1,000 milliliters in 1 liter. Okay, so keep that straight. The other catch with molarity is it's moles of stuff divided by volume of the solution. Okay, that's not volume of the water that you add. Those are 2 different things. We'll talk about that in a little bit. So it's moles of stuff divided by the total volume of the solution. Okay, now let's do a sample problem. Let's say you needed 2 molar sodium chloride solution, 100 milliliters of that. How would you make that? What would you do? Okay, well, the first thing we have to do is we have to figure out how many moles of salt we need, because we know the molarity and we know the volume. That can give us the number of moles. Second thing, we have to convert that moles of sodium chloride to grams of sodium chloride. And to do that, we've got to go to the periodic table and get the formula mass. So let's do that. HCl are needed to make 100 milliliters of a 1 molar solution. One thing you got to remember right off the bat, 100 milliliters is equal to 0.1 liters. Okay, you got to go to liters. All right. And the other thing to remember here is we have one equation here that the molarity is equal to the moles divided by the volume. Okay. Now, the first step is we have to figure out how many moles. In order to make this solution, we have to figure out how many moles of sodium chloride we need. So moles is equal to molarity times volume. The molarity is 2 molar. The volume is 0.1. So we need 0.2 moles of sodium chloride. Okay, piece of cake. Now, the thing is, though, molarity is not grams. So this gave us the moles. We can't measure moles, right? So we need to know how many grams that is. In order to figure out how many grams that is, we have to know the formula mass, right? So we go to the periodic table. Sodium is 22.99. Chlorine is 35.45. Add those up. 58.44 grams per mole. So that's step 2. Now, what we can do in step 3 is take the 0.2 moles and multiply it by 58.44 grams per 1 mole, and that turns out to be 11.7 grams of NaCl. So we would need to mix 11.7 grams of sodium chloride and then add water until we get 100 milliliters. Okay, so that's great. Now we know what mass of sodium chloride we need. How are we actually going to make this? What are we actually physically going to do? We're not going to do much of this in our labs, particularly since we're not going to even be in a lab anymore, right? But when you get to college, you have to do this, and you'll use this thing called a volumetric flask. I think these are kind of cool looking, got a cool shape to them. Make great flower vases if you're a nerd. This is a volumetric flask. It's, we have graduated cylinders with all those lines in it, and you can measure out all those volumes. This is can measure 1 volume. this line right here, I'm not sure if it's clear enough to see. That one line right there is 100 milliliters. It's a one-trick pony. That's all it can do is measure 100 milliliters. But it does it very accurately. This line right here is actually etched on there, and it's very accurate. These are all over the place in chemistry labs. You use them all the time to make solutions. So what are we going to do to make this 100 milliliter solution that we need? Well, I've already measured out. Here's the salt. I've already measured that out. So you put that in first, and then you add water to it. And now, the thing you have to be careful of is as you add the water, you don't just start throwing the water in there. Usually you maybe go about to there, I don't know. And then you got to swirl it a little bit. And you're probably going to have to let it sit. You've got to make sure that all that salt dissolves before you go on. Because as long as that salt's there as a solid form, it could mess up your volume. And so you got to wait for your salt to dissolve. Now I don't want to wait. So, whoa, look, it's all dissolved. Cool, huh? And then what you do, use your imagination. And then what you do is then you start to add the water, and you got to be careful here. You don't want to try to fill it up to the line with this, okay? The real bummer is if you go over, you have to start over again, right? Because there's going to be salt in that water already, and if you take some back out, now you're off, right? So do not go over. Your lab partner will get very mad at you. What you need is this thing. It's called a pipette. I like to call them pipettes because it's kind of fun. Pipette. Well, I actually had a student come back to me and said her lab instructor laughed at her when she called it a pipette. So, sorry. But by the way, I do want to point out that she heard the lab instructor sometime later in the semester use the word pipette, so she thought that was pretty cool, even though he laughed at her. He was using the term pipette. It's kind of fun, right? Pipette. So what you do, you use this guy to fill it up to your line, and remember, we've got this meniscus deal. That's that curved part. You got to get that curved part right at the line, not the edges, the lower part of the meniscus. And we are there. So what we've done, we now have 100 milliliters of a 2 molar solution if I had waited for all the salt to dissolve. Still some down there, but. And ta-da, we've made a solution. One thing I got to see that we didn't do is we didn't fill this up with water to the 100 milliliter mark and then add the salt. All right, think about it. If you get 100 milliliters of this and then add the salt, you've just changed the volume. Remember, molarity is moles of stuff per volume of solution. So you can't put the water in first and then add the salt. You don't have 100 milliliters of solution anymore. So got to be careful with that. Now, problem number 5. I'll leave you to do that. But basically, in this case, we needed 2 molar solution. How many grams of sodium chloride do we need? Okay, number 5, just turn it around. We added so many moles of sodium chloride. What's the molarity of the solution? Okay, so it's just backwards. Nothing big about that. And then number 6 is same as 4. I'm sure you can do that, no problem. Number 7, things get a little trickier here. Well, not trickier, fun, right? Here's the situation with number 7. I can't read this writing here. I don't know what yours says. I think, all right, you're doing something and you need 2 molar solution of an acid, sulfuric acid. So you need a 2 molar solution. You don't have 2 molar, you only have 18.8 molar. And I think that's like pure, well, no. That's the most concentrated sulfuric acid you can have is 18.8. It's nasty stuff, don't mess with it. But that's all you have is 18.8. And you need 2. Well, what are you going to do? Well, you could probably think about this. If we dilute that 18.8 down enough, we'll end up with 2 molar. Right? Now, we don't want to dilute the whole jug of 18.8, though. I mean, that would be silly. We only need 0.75 liters. So the question is, how much of the alcohol, of the sulfuric acid, do we need, and how much water, when mixed together, will give us 0.75 liters of a 2 molar solution? Okay, so this is basically the same problem as the first hand sanitizer problem. But instead of dealing with volume of alcohol, we're dealing with moles of stuff. Okay, so it's the same idea. Okay, so yeah, this is kind of like that first hand sanitizer problem. All right, so again, we're going to list the variables, but again, it's going to seem a little bit waste of time, but I think it's important. So the first thing is, remember we have two acids. We need to know the volume of the 18.8. We don't know that. And the molarity of the 18.8 is 18.8. Oh, that's kind of hard to see. 18.8 nets moles per liter. And then we have the volume of the water, right? And we don't know that. And the molarity of the water, there's no acid in the water. The molarity of the water is 0. Right? And then we've got the volume total has to be 0.75 liters, and the molarity total has to be has to be 2 moles per liter, 2 molar. Okay, so again, it's the same idea. The total number of moles from the concentrated acid plus the moles from the water have to equal the moles in the desired acid. So the total number of moles that we need is 0.75 times 2. The moles we get from the concentrated acid is the volume of the 18.8. We don't know what that is. And the molarity of the 18.8 is 18.8 plus the volume of the water times the molarity of the water is 0. So obviously that goes away. And then the volume of the 18.8 is again the ratio 0.75 over 18.8 times 0.75, and it's 0.08 liters of the 18.8 and 0.67 liters of the water. And we mix those together, that gives us 0.75 liters, and it's going to have a molarity of 2. Okay? Okay, on number 8, the idea here is you have 17 molar and 2 molar acetic acid, but you need 3 molar. So the question is, how much 17 do you mix with how much 2 molar to give you a half a liter of 3 molar? Okay, now I know some of you smarty pants are saying just dilute down the 17 molar, and that's all you got to do. Why worry about the 2 molar? I don't know. It's more of a fun problem with it. And the other thing, use your imagination. Maybe that 17 molar is really expensive and you want to use as little as possible. Or maybe you're almost running out of it. You don't have enough of it. And so, I don't know. Don't let that stop you. But this is the same as our second hand sanitizer problem now, right? And again, but instead of keeping track of how much alcohol you get from each, you keep track of how many moles you get from each. So it's nothing real different, okay? And then finally, that try this problem. And by the way, try this. It's not a suggestion. Yeah, you have to do them. It's, I don't know. Should maybe call it something else. So don't think it's, oh, try this. I don't want to try it. It's not optional. Just do the problem. But it's a fun one. It comes from food science. And at the end of the year in food science, we make ice cream. And one of the things that comes up is there are a real wide variety of different dairy products with different amount of fat in them, light cream, heavy cream, full milk. It's just, there's a lot of them in different countries. It's different. So, and it turns out you need, say, a 12% fat ice cream mix, right? But you don't have anything that's 12% fat. You only have 2% low-fat milk, and you have 35% cream, heavy cream. So how do you mix the 2% low-fat and the 35% cream so that you end up with 2 liters, I think it is, of a 12% fat mix, right? It's the same thing again, right? Don't let what you're dealing with confuse you. With the hand sanitizer, we were talking about volume of alcohol. With the acids, we were talking about moles of acid. And now we're just talking about grams of fat. So It's nothing incredibly different. So have fun with that.